In the module 4 of the fluid mechanics, that is the topic of orifice and mouthpieces. Even the weir and the notches are also included in this topic. Basically the purpose of this particular topic is to study the basic flow and its flow measurement. In fact, whatever the fluid measurement is there, so that this particular orifice is a very useful tool to measure the flow of the water. In fact, in a fluid dynamics, we are going to measure the volumetric flow, that is also known as the volume flow rate, or the rate of the flow, or the volume of the velocity, what we can say. That is nothing but the volume of the fluid which passes through the given surface per unit time. And in general, in our SI unit, we'll put it in the form of the so much of meter cube per second, that is a cubic meter per second. And usually it is represented by the symbol Q, that is the discharge. And this particular this orifice is a very convenient method to measure the flow of a fluid. Apart from the orifices, there are other this one's method of the finding the discharge are like mouthpieces, notches, and the weirs are also there. Okay, so here first we'll see about in this topic related to the orifice. Okay, so actually the orifice, you can see it in the figure. The orifice is nothing but the opening at the side or at the bottom. You can see the first figure. You will notice that there is the opening at the side of the wall of the whatever the vessel or a tank is concerned. Okay, and under next figure, it is at the location is at the bottom side. Okay, at the bottom side we can notice that there is a opening. So in general, the orifice is nothing but a opening in the side or a bottom of a vessel or a tank. So this opening is useful to measure the discharge of the fluid. So this is all about the orifice is concerned. Now let us see that the classifications of orifices. So this classifications of the orifice is mainly classified based on the position. That is, number 1 is on position, number 2 is on size, number 3 on shape, and number 4 on the edges, and number 5 on the discharge. So let us see one by one. Okay, so first the position. Okay, whatever the position is there. So how this the orifice is located, whether it is there in the side or whether it is in the bottom. Okay, just in the previous figure we have seen that the location or the position is at the side of the vessel or a tank, or at the bottom of the tank is concerned. Now next the whatever the thing is that it is on the size. Okay, it is of the size, based on the size. So this size may be a small or it may be a large. Okay, size may be, we can say that orifice is a small or a large orifice. So how it is going to be differentiated? So when the dimensions of the orifice, whatever the diameter to depth ratio is less than head of the whatever the causing flow, so that is whatever the depth is there. Okay, so depth is there, so it is D is less than the H, whatever the head, whatever the diameter is there, so it is less than the head. Okay, so that the classifications, we can say that the small one, whereas other hand the large when the dimensions of the orifice is greater than. Okay, so whatever the dimensions of the orifice diameter is greater than the head of the water. Okay, whatever the head of the water above the level of the orifice, what we say that h. Okay, so if it is the greater than that height, so in that cases we can call that one as a large one. And next, the third, whatever the classification of the orifice is there on the basis of the shape, whatever the shape is there. The first one is the circular shape. You can see that circular in shape, cross section is a circular type, or under maybe a square, whatever the cross section is there, if it is a square type. And next, if the cross section is a rectangular shape, okay, it may be a rectangular shape, or even it will be a triangular shape. Okay, based on the shape we can have the cross section, whatever it is there, circular, square, rectangular and triangle. So like that the classifications are made. Then next, the fourth, whatever the classification is there, next to the whatever the classification is there based on the edge. Okay, so here the edge may be a sharp edge. You can see that whatever the orifice opening is there, top as well as the bottom, the whatever the edges are there, so they are of a sharp edge, and next, whatever it is a square edge, you can see that whatever the opening is there, it's a square shape. Okay, and the third, whatever the edge, what we can notice is a belt mounted. Okay, it is a belt mounted, means you can see that the smooth faces at the outer side, whereas the sharp, whatever the edge is there at the inner side, so that is called as belt mounted. Okay, next, lastly, whatever the fifth classifications of the orifice is there, so it is based on the discharge. Okay, how the discharge is going to takes place. So the first, whatever the figure, you can see it here. Okay, so here in this figure we can see that the whatever the fluid is there, it is a freely flowing into the air. Okay, so whatever the water is there, gradually it is going to be flow through this orifice. When the orifices get opened, so it is free to flow in the atmosphere. But whereas the second one is partially submerged. You can see that whatever the orifice position is there, so it is a partially in water, in the fluid. Okay, partially it is a fluid. Okay, partially it is in the left side, it is whatever the water tank is there, but whereas in the right side, whatever the fluid is flowing, so it is a partially submerged. Okay, whatever the position of right side flow is there, it is a partially submerged. And next one, you can see that whatever the water level is there, right, in the right side, it is above the right side, above the whatever the level of the orifice is there, above the level of the orifice, so that one is fully submerged is there. So like that the classifications are made, classifications of the orifices are made. Next, we'll see one important parameter which we should know from the orifice, that is a flow through the orifice. So that one is a vena contracta. You can see that in the figure, you can notice that suppose a sharp circular edge orifice is there, okay, inside the tank, okay, which it will discharge the liquid directly into the atmosphere. You can see that directly it is discharging the whatever the liquid is there into the atmosphere. In the figure we can see. And when the jet of the orifice is converges, you can see that at convergence means whatever the diameter is there, it is going to reduce. Okay, so whatever the orifice is there, so when it is the jet of the fluid is coming out from the orifice, so it will converge to a minimum cross section. You can see that a minimum cross section at xx. In the figure you can see that at xx there is a minimum cross section, and then diverges again the diameter is going to increases gradually. The cross section is reduced, and suddenly gradually there is a increase in the size, and this whatever the reduced cross section is there, okay, so that particular point is called as a vena contracta, means the section at which the cross section area of the jet, okay, vena contracta is nothing but the section at which the cross section area of the jet is minimum and less than the orifice diameter. You can see that orifice diameter is this much, and at xx it is reduced, and that particular point is called as vena contracta. So this is all about the Venn contractor, how orifice will create a lesser diameter at the jet level. So that particular point is called as Venn contractor. Now here let us see that what are the things which we can notice over here at A point. At A point means at this point, and B is at the Venn contractor level. Okay, so B is exactly at the center level of the orifice. Okay, and as well as the Venn contractor, and A is a point where it is a top of the surface of the water level. So this is a point and this is a B point, and whatever the height of the water is there, so that we can see it as a H. Okay, so based on this, we'll see the some of the things at point A as well as at point B. So since the pressure at A is 0, because both A and B both are at the level of the atmosphere, so that's why no pressure is there at point A as well as at point B. Okay, so now here at the A, the velocity is 0. At point A, well, the velocity is 0 because it is open to atmosphere, and at B there is a flow of the fluid is there, so that's why the velocity at B is hs. And whatever the potential head at A, is head of the water, whatever it is, H is there. Okay, so that is ZA is H, whereas ZB is the position at the level of the orifice, so that's why that head will not be there, potential head is not there, so that is a 0. Now according to the Bernoulli's equations, whatever the Bernoulli's equations at A as well as B are both constant. So according to this, let us say that A means here it is a 1 position, and B is nothing but here the position the 2. Okay, so according to this Bernoulli's equations, we are having the P1 by rho z plus V1 square by 2g plus Z1 is constant at the B point, that is a P2 by rho g plus V2 square by 2g plus Z2. Okay, both are the constant according to the Bernoulli's theorem. Now let us put all these point A and point B values in the Bernoulli's equation. So in this case, the P1 the part is 0, and Z1 is nothing but H. Okay, and V1 part is also 0, and whereas P2 part is also 0, the V2 part is there, but whereas Z2 part is 0. So now if you substitute in this values of the whatever the point A and point B, so obviously you will going to get this only the V square by 2g is equal to H, means whatever Z1 is exist and V2 the part is exist. Now the velocity at B, based on this, the velocity at B point is calculated as square root of 2gh. This is a very important. This VB is nothing but a theoretical velocity. This is a VB is a theoretical velocity. VB is equal to 2 root gh, means whatever the velocity at the B point is nothing but whatever the head if you are having. So if you square root of 2gh, so you definitely will going to get the theoretical velocity, whatever it is there, theoretical velocity, what you can get it from this relation. Now next part is the hydraulic coefficient. So in this this orifice topic, these three things are very important. That is the hydraulic coefficients, means whatever the coefficient is because of the velocity, that is a coefficient of velocity CV we will call, and whatever the coefficient of contraction. Okay, so that based on the area, the coefficient of the contraction we call it is a CC, and the coefficient of discharge based on the discharge. Okay, so we'll call that one as CD. Okay, so let us see that what exactly the three constants CV, CC and CD deals with. So the first one is CV. CV means here it is nothing but the actual velocity. It is a ratio of actual velocity to the theoretical velocity. So actual velocity means at jet point, it's a VA. Okay, actual velocity at the jet point is a VA, and the theoretical velocity is root 2gh. Okay, just now we have seen that is both ratios will gives us the coefficient of velocity. Next one CC, that is a coefficient of contractions. It is mainly due to the whatever the two areas are there, actual area at the Venn contractor AC and actual the whatever the area of the orifice is there. So ratio of area of the both the vena contracta to the area of orifice. Obviously, the area of the whatever the AC is there, that is a vena contracta, will be always less, because we have noticed that the cross sectional area at AC is less as compared to the diameter of the orifice. Similarly, the CD means the coefficient of the whatever the discharge. So here it is actual discharge to the theoretical discharge, So here actual discharge will be again it will be less as compared to the theoretical discharge, and similarly actual velocity is also less at the jet to the theoretical velocity. So that's why all these whatever the CV, CC, CDs are there, so they are the less than 1 only, because that actual values are less as compared to the theoretical or the values. So that's why they will be always less. So all this CD, CV, CCs, the values will be always less. Always it will be less than 1. Based on this, so we'll see some numerical examples. So how this whatever the various relations in the orifices, which just now we have seen, and how it will be helpful for solving the numerical examples is concerned. The first whatever the numerical example is there. So here what it says is that the head of the water over the center of the orifice of a diameter is 20 mm in 1 meter. Okay, so the actual discharge through an orifice is 0.85 liter per second. So find the coefficient of discharge, means the CD, how much it is there. So based on this, you can see that from the given data, so the diameter of the orifice is known. How much it is? It's a 20 mm. Okay, and what is the head? Head is 1 meter. Okay, so that's why the diameter D is equal to 20 mm is there. So for the convenience of the uniform units, just convert into the meter. So the whatever the 20 mm is there, so it will become 0.02 meter. And similarly, whatever the diameter of the orifice we have calculated, now its area. Okay, its area, cross sectional area, is nothing but pi d square by 4. Okay, the diameter we just substitute, and now we are going to get the cross sectional area pi d square by 4. So that is going to 0.0000314 meter square. Okay, and now the head, whatever it is there, head is available 1 meter. Next point is the whatever the discharge is there. Discharge is given. Actual discharge, it is actual discharge is with the Q is equal to 0.85 liters per second is there. So it's a in the form of liter is there, but we need to convert in terms of meter cube. Divided by 1000, you do it, so that you will going to get so much of meter cube per second, that is a 0.00085 meter cube per second. So these are the sum of the given datas we have converted into the some required units. Now let us see that how this the CD, the coefficient of discharge, is to be calculated. Now first we should know that the actual discharge as well as the theoretical discharge. Actual discharge is given to us. Now we have to calculate the theoretical discharge. To find out the theoretical discharge, so first we should see that what will be the theoretical velocity. And anyway, the theoretical velocity is nothing but square root of 2gh, the head of the water above the level of the orifice is given. H is equal to 1 meter. So now you just substitute square root of 2gh. So you will going to get the theoretical velocity as 4.429 meter per second. So this one is the theoretical velocity. Now based on the theoretical velocity, the theoretical discharge is nothing but the theoretical velocity into cross sectional area of the orifice. So theoretical velocity is just now calculated, as well as the orifice cross sectional area is also known. So both the product of that velocity into area of the orifice, you will going to get the Q theoretical, that is a discharge theoretical. So that is calculated as 0.00139 meter cube per second. Now this is a theoretical discharge. So now what is the coefficient of the discharge? Coefficient of the discharge is given by actual discharge to the theoretical discharge, that is a CD. So CD is nothing but 0.00085 divided by 0.00139. So now you just see that whatever the answer is there, 0.61, which is obviously less than 1. Okay, so all the CV, CC, CDs are always less than 1, always less than 1. That point you should note. Okay, now let us take the another type of the example, another type of the numerical example. Let us read out the example. The head of the water over an orifice of a diameter 100 mm is 10 meter. Okay, the water coming out from the orifice is collected in a circular tank of diameter 1.5 meter. The rise of the water level, okay, is in tank whatever it is there 1 meter in 25 seconds. Also the coordinates of the point on a jet measured from the Venn contracta are 4.3 meter horizontal and 0.5 meter vertical. So find the coefficient CD, CV and CC. So all the three things we supposed to calculate. So here in this problem you can see that the orifice diameter is given, that is 100 mm is there, and whatever the head of the water is there 10 meter above the orifice level, the head of the water is 10 meter, and whatever the water is coming out from the orifice is there, it is collected in a measuring tank. So that tank diameter is 1.5 meter. That tank diameter is 1.5 meter, and because of this whatever the fluid is coming or water is coming out from the orifice is collecting in a tank, so obviously the water level in the tank is going to increase. How much it is going to increase? For a 1 meter it will happen in a 25 second, means in a 25 second 1 meter the water level is raised. So now we can see that how much the discharge is taken place. Okay, this much of the size of the tank is there, and this much of the time is there, so that we can find out the discharge which is going to take place, which is happened in a water tank, that is so much of meter cube per second, that we can easily find out. Then also it is said that yes, the coordinates of the point at the jet, okay, at the Venn contracta, they are the points are measured. How much it is there? X is equal to 4.3 meter and Y is equal to 0.5 meter. Means X means the horizontal whatever distance is there, and Y is the vertical distance is 0.5 meter. And with this you will see that how this things of the CD, CV and CC is to be evaluated. Let us see that as usual the given data is to be maintained in the same unit. So here head is in 10 meter, head of the water is 10 meter, H, that is 10 meter, whereas the diameter is in terms of mm. So that we have to convert that the diameter of the orifice in terms of meter, that is a 0.1 meter. Now the cross-sectional area, whatever the cross-sectional area is there, pi d square by 4 of the orifice, cross-sectional area of the orifice. So that is works to 0.007853 meter square. Now whatever the measuring tank is there from the orifice, whatever the fluid is there coming down collecting in a measuring tank, so that diameter is known. That the container, whatever measuring container is there, the diameter is known as 1.5 meter. Now its cross-sectional area, obviously it is a pi d square by 4, pi d square by 4. So now that area of the measuring tank is becomes 1.767 meter square, and at the same time we have noticed that this whatever the measuring tank is there is going to raise a water of 1 meter in a 25 second. So that's why whatever the height of the rise of the water is there in the measuring tank is a 1 meter, and for that it took 25 second. So definitely we can find out the quantum of discharge. Okay, now here whatever the horizontal distances at the same time is also given as x is equal to 4.3 and whatever the vertical distance y is equal to 0.5 meter. So now based on that now the whatever the theoretical velocity we can calculate, as root 2 gh. Okay, so based on this the theoretical velocity is root 2 gh. The head of the water is known, So we can easily find out the theoretical velocities is going to get as a 14 meter per second, and at the same time the theoretical discharges can be also calculated. Theoretical discharge is theoretical velocity into cross-sectional area of the orifice. So both are calculated. You just multiply both the area of the cross-section of the orifice as well as the theoretical velocity. You will going to get the theoretical discharge. Theoretical discharge is works to 0.1099 meter cube per second. Okay, and now actual discharge, whatever is happening in a measuring tank, so that actual discharge is nothing but the cross-sectional area of the measuring tank into the height of the water is raised to the with respect to time is 25 second. So now A into H, that is the area, cross-sectional area, how much the water is raised, 1 meter, and for that 25 seconds will takes. So that's why you will going to get the actual discharge. Actual discharge is 0.07068 so much of meter cube per second. Whatever the actual discharge is, 0.07068 so much of meter cube per second. Now what is the CD? CD that is a coefficient of discharge. Coefficient of discharge is actual discharge to the theoretical discharge. So actual discharge is also known, theoretical discharge is also known. So we can have the CD, the both ratio is 0.643. Okay, now also we have to find out the whatever the CV is there. Okay, CV we have to calculate. So this CV is nothing but x divided by square root of 4IH, whatever the CV, the coefficient of the velocity. So that is the x is given, the horizontal dimensions is 4.3 meter, and 4YH is there. Y is also known, H is the height is also known. So with this we are getting as 0.96, and the last whatever the CC is there, CC is nothing but the ratio of CD by CV. CC is nothing but ratio of CD by CV. So CD is also calculated 0.643 and CV is 0.96. Whatever the ratio is there, that is works to CC 0.669. So now you can see from all the three, whatever the CD, CV, CC, so all are less than 1. Whatever the coefficients are there, they are less than 1. Okay, so that which we can notice from this example. Now let us move into the next example. Here in this example, it says that a tank has two identical orifices, one of its vertical side. Okay, so you can see that orifice number 1, orifice number 2, identical orifices, identical, both the diameters are same. Okay, now the upper orifice is 3 meter below the water surface. You can see that from the figure, whatever the orifice number 1 is there, its location is 3 meter below the water surface. Okay, and the lower one is 5 meter below the water surface. The second one, whatever the lower one is there, it's a 5 meter below the water surface is there. So these are the locations of the orifice. If the values of CV for each orifice is 0.96, whatever the CV, coefficient of velocity, is 0.96. So here it is asked that find the point of intersection of the two jets. You can see that the point of the intersection means whatever the x position as well as the y position also. Okay, that is the y position will be measured. One is y1 is measured from one orifice and y2 is measured from the second orifice. So that one will be the position of these, whatever the jet of water are there. So they are at some point, they are meeting, So we should know that what exactly the value of x, what is the value of y1, what is the value of y2. So that is the problem is there. Okay, so now let us see that one by one. So here from the figure we can notice that for the orifice, whatever the head of the orifice 1, H1 as 3 meter, and similarly head of the orifice 2 is H2 is 5 meter, and CV for the both orifice is given as 0.96. Okay, now based on this, so we'll see the positions of this intersection P. So whatever the intersection P is there, so we can see that the x is the horizontal distance and y1 or y2 are the two vertical distance for the respective position of the orifices. And anyway, whatever the y1 is there, the location of the first orifice to the point P, so that is nothing but y2 times of the difference of the two heads, whatever the h2 minus h1 head is there. So that's why it is a y2 plus 2 meter, whatever the y1 is there, y2 plus 2 meter. From the figure you can see that whatever the y1 is there, okay, whatever the y1 is there, it is nothing but y2 plus whatever the difference of two heads are there. Y1 is nothing but y2 plus 2 meter, whatever the difference of 1 and 2 is 5 minus 2, that is 2 meter. Okay, so that is the meaning of the y1 is equal to y2 plus 2 meter. Now anyway, for the two orifices, the CV can be put it separately, that is the CV1 for orifice 1, CV2 for orifice 2. For the both cases, we can put it the equations as x divided by square root of 4y1 h1. So here y1 and h1 are the vertical as well as the heads of the waters, okay, vertical locations as well as head of waters. So here we'll put the y1 as it is. Similarly, x is also unknown, put as it is. Now for the orifice 2, whatever the y2 is there, okay, so and h2 is there, h2 is also known to us. So now you just put it x and y2, or they are unknown, you put it in the same the whatever the values. Now here since the both are identical, whatever the CVs are there, so they are also same. Coefficient of the velocities are same, since because of the identical. Now whatever the CV's equations are there, that we can put it the CV1 as well as the CV2. And now here you can see that there is a one relations. In the previous case we have seen that y1, whatever the y1 value is there, it's a y2 plus 2 times is there. Okay, so now whatever the two the equations we have done, equated the CV1 is equal to CV2. From this after simplifications we arrived as 3y1 is equal to 5y2 is there. So now what we can do, so we can substitute wherever the y1 is there, okay, you can substitute as y2 plus 2. So 3 times of y2 plus 2 is equal to 5y2. So you can see that everything is in terms of y2 only. Now simplify, the y2 can be calculated. Once a y2 is calculated as a 3, then obviously the y1 is 5 meter. Okay, now here from the previous whatever the CV2 equation, we are having the x divided by 4y2 into h2 is that. Now y2 is also known, h2 is also known, CV is given, both are identical, that is a 0.96 is given in the problem, it is there already. So now x is the only unknown, So now you substitute in this x, and we can have the simplifications of this one. So we're going to get x is equal to 7.436 meter. So now the locations x as well as the y1, y2 are calculated from this particular example. That is a location of the point where exactly the two jets of the waters coming out from the orifice are going to meet. So that is the problem which is asked here. Now let us take the another example. Okay, another example. In this example, it says that the closed tank partially filled with water up to the height of 0.9 meter. Okay, so here the water level is is 0.9 meter above the orifice. Okay, and whereas the orifice is of diameter 15 mm. The orifice diameter is 15 mm at the bottom of tank. Its location is at the bottom of tank. The air is pumped into the upper part of the tank. Whatever the air is there, it is pumped into the upper part of the tank. Determine the pressure required. For a discharge of 1.5 liter per second through a orifice. Okay, whatever the discharge is there. So this much is 1.5 liter per second. And whatever the CD is there, that is a coefficient of discharge. Is there. So it is 0.62. Okay, now let us write down one by one the given data. So here the whatever the water the level from the level of the orifice is h, that is the head of the water above the orifice, is given as 0.9 meter, and diameter is 15 mm of the orifice. So that whatever the is in the mm is there, you just make it in terms of the meters conversion. So diameter is converted as 0.015 meter. Now this whatever the cross sectional area of the orifice is nothing but pi d square by 4. So that is works to 0.0001767 meter square. That is the cross sectional area of the orifice. Now the actual discharge is given is 1.5 liters per second is there, liter per second is there. So we need to convert in terms of so much of meter cube per second. So just divided by 1000, so that we will going to get so much of meter cube per second, that is a 0.0015 meter cube per second. Anyway, CD is given 0.62. Now with the continuation of these available data, now whatever the pressure is there, okay, pressure of the air, so that the pressure head is given as P by rho g. So here whatever the P is nothing but the pressure, P is the pressure. So that rho means the density of water is 1000, okay, and G is 9.81. you just put it in this equation, both P in terms of P only, the pressure head. Now whatever the velocity is there at the outlet of the orifice, that is whatever the water is there coming out from the orifice, so that V2 is given by square root of 2g into h plus P by rho g, whatever the equation is there. So in this equation you just substitute the values of h as well as the whatever the P by rho g you just now calculated, you just substitute over here, and that will be the V2 put as it is. And now the discharge, whatever the discharge is there, okay, so that discharge is given by Q into CD into cross sectional area of the orifice into velocity, okay. So CD is given, discharge is also known, okay, and here the remaining thing is the only the P, whatever the P is the only unknown, so now that solve for the P. So after simplification, the P is works to 9.125 Newton per centimeter square. So whatever the pressure at the air, which is going to be pumped in this system, so that is works to 9.125. So like that the pressure is to be calculated from this figure. Thank you.